Good morning, everyone. I'm Sue Graham-Johnston. I'm the president here at 128 Technology, and I want to add my warm welcome to Tom's introduction. Thank you all for traveling here to be with us. And we've got an exciting day full of technology and full of helping you understand how our product is solving some really fundamental problems in the networking world today. So our thesis is that companies actually use networks to deliver applications and services. They actually don't want to worry too much about the network itself. And when you focus on that and you're dealing with the challenges of cloud and mobility and security, you recognize that the network is actually misaligned with how companies want to use it today. And we've got a team full of serial entrepreneurs and diehard technologists that really stepped back and took a deep look at this problem and understood that if we just reorient networking to focus on the session, we can get rid of about 30 years worth of technology workarounds and overlays, simplify the network itself, and help businesses achieve their goals. So we've been around for 5 years. We hit our 5-year anniversary this month in July. And with that, we've been delivering continual innovations. So now when you face some of these challenges, whether it's a skinny pipe and dealing with the fact that current technologies add a lot of overhead to that, or dealing with high bandwidth applications and managing the fact that things get locked onto a single core, we've effectively innovated around many of those problems and are able to deliver a single technology that scales from very low bandwidth to very high bandwidth and actually works and implements security frameworks and application delivery, whether you're in the cloud, whether you're still on-prem, and no matter what applications you're delivering. So we have a full team of folks today who are going to talk to you about what our technology does, how it works. So in the morning, we'll go really, really deep on what we do and how it all works. And then in the afternoon, you'll see lots of demos about how it's applied and the different problems that we solve. So with that, I'm going to turn it over to Ritesh, who's going to talk you through an overview on the company and more about our technology. Thank you. I hope you guys have a great day.
Good morning, everybody. My name is Ritesh Mukherjee. I'm going to walk you through an overview of the product, what the product does. My job is pretty easy today. I only have to tell you what it does, and then there'll be some other guys who will tell you how and everything it works. And you guys can ask the more tough questions at that point. But having said that, I'm going to give an overview of why we are different, what we do, and so on. First of all, what we make. We make session-based software routers. We make only software routers. Our routers run on any of the hardware. They leverage capabilities of the hardware and, of course, achieve line rate forwarding. Why we are different from any other company or any other networking company is because we are session-based. Routers in general, they forward packets when they get them. They learn routes. They forward packets. If you want to block things in certain directions, you put ACLs. You want to change things, you make tunnels. You want to add other capabilities, you service chain things. In our case, we are session-based in the sense we keep track per flow, which routers don't do. They are stateless. In our case, we are stateful. And the advantage of doing that is we are able to collapse all other functions into the router itself and also achieve a lot of other benefits. I'm going to talk about some of these benefits and some of the high-level capabilities of what the product does. First of all, why we decided to make something which is very different. The reason is the age-old, like Sue mentioned, the age-old paradigm doesn't work anymore. Networks have changed. User data is now everywhere. We regularly face questions from people like my data is in Slack, is in Google, is in ServiceNow, Office 365. How do I protect everything? Also, the way people operate has changed. Earlier, it was easier to have walled gardens. And the reason was you had big computers which were placed in branch sites. You didn't take them out. You didn't move them around. It was easy to, create a perimeter. Today, you can't have a perimeter mainly because you have laptops, you have mobile phones. People are using these. They move around. They work from home. They work from Starbucks. We actually have our developers here. They work from a coffee shop. They come back in. They plug the Ethernet cable into the data center and start working. Well, they just bypass the firewall if they do that. And we want to prevent these kind of things from happening. Also, organizations are moving their data into public clouds. One of the advantages of doing that, obviously, is you get all the benefits of resource sharing and everything else. But also the disadvantage is everyone does things a slightly different way. So now you have a problem of having consistency with regards to security, policy management, and so on in public and private clouds. We want to solve that. And of course, the world is moving towards white boxes. Today, the capabilities we get from white boxes is far superior to what we can get with even ASIC-based hardware. And I'm going to talk about how some of these companies who have used white boxes, why we believe also why that's the right way to go, and that's the right way to deliver software. If you look at how the network has been built, traditionally you had routers, which were stateless. I just spoke about it. They forwarded packets. If you wanted to do something special, like block things in certain directions, you added firewalls. If you wanted to move loads in one direction over the other, you added load balancers. You wanted to find out what these things do and what they mean, you added deep packet inspection. And finally, if you wanted to move things in one direction over the other, you added tunnels. Tunnels help you build, pathways which allow you to not follow traditional routing but do special things. What we noticed is every other than the router, every other device in the network that you're adding keeps state, and it works on flows rather than working on packets alone. What we decided is if we can add statefulness to the router itself, we can collapse all of these middle boxes and all of these functionality into the router itself. By doing that, we'll be able to make the router more intelligent. We'll be able to achieve further benefits, like we don't use overlays, we don't eliminate tunnels, bandwidth savings, very high scale, very high performance, and of course you eliminate costs and lower power usage and everything else as well. So how did we do that? We added 4 capabilities to the router. But before that, we look at things as sessions. For us, all communication between any 2 parties in the internet or on the network is a session. For example, a conversation between me and YouTube is one session. I ask YouTube to send me packets, and YouTube sends me packets. That's one session between me and YouTube. That's a valid session. If YouTube sends me packets without me having asked YouTube to send me packets, that's an attack on me. We can learn many things from sessions this way. Sessions can be directional. They can have source and destination IP addresses. They also have a lot of capabilities which enable us to perform different tasks on them. We believe that the network exists to deliver sessions, which is applications and services, and that's how you should configure networks. We've also changed the way we configure networks. Rather than having 10.10 talk to 1.1 all the time, we follow service-based models for forwarding traffic, and I'll talk about that in a little bit. We have done 4 things to enable things in the router. I'm going to talk about this, and then I'm going to talk about how we apply that in the network itself. We have made the router session-aware, which means we keep state per flow. It's a transient state only maintained during the duration of the flow. This tells us many things. For example, it tells us source and destinations. We can do directionality. We also understand many things based on session state, and we forward based on this state. The router, we run existing traditional routing protocols like BGP, OSPF, ISIS with other routers in the network. We learn all routes from them, but we don't forward based on those routes. We forward based on what the service tells us, in the sense what these sessions tell us. For example, you can create a service saying, give sales access to Salesforce, and you can have some sort of SLA associated with it, and we would follow that SLA. We would create a state when we see a packet going towards a flow going towards Salesforce, and we would forward based on that state. I'll go through a packet walk to say how we do that as well. We have made the router service-centric. In the sense, it's similar to intent-based networking, but having said that, what we wanted is, instead of having tunnels talking to 10.10 to 1.1 all the time, we wanted to make routers work as services so that they followed your business policies. For example, if you wanted to have the same example, if you want sales to talk to Salesforce, you can define a service saying Salesforce is located on the internet. And you just tell all the routers, hey, give sales access to Salesforce, and they all understand that whenever sales traffic comes in, they have to send it towards the internet because that's where the service is located. It's service-based, it's name-based. The advantage of doing that is every time you make changes in the network, you don't have to go and configure IP addresses again and again. You can do it by using names. Waypoint settings. We wanted to control the paths in the network just like you do with tunnels, but without, of course, having the overhead and creating tunnels. We do that by using waypoints. Waypoints are basically the interface IP address of the router itself. It's the IP address of the interface on the router. And by following these IP addresses, we can create a path in the network, similar to segment routing, but without any overhead. The routers keep state on how to forward this traffic, and they do not add any overhead on the packet itself. It'll be clear when I do the packet walk in the next slide. And finally, we wanted to establish a logical connection between two entities in the network. We do that by using an intelligent cookie, which we add only in the first packet, and it's called metadata. We add it to the payload section of the packet, and that tells the other side what's the logical understanding between these two routers. We never have to send that metadata again because the routers keep state and they forward based on that state. These are the 4 things which enable us to do many cool things in the network, and let's go and talk about how we do that. I'm going to do a packet walk to explain what is secure vector routing. We call it secure vector routing because obviously it's secure, it's a secure connection, it has directionality inbuilt. We can also do encryption and authentication via FIPS 140-2 certification. And it's vectors in the sense it's directional, so that's why we call it secure vector routing. That's the way we forward packets. Let's look at how we would do that. Let's say you have a source and destination. You want to send packets from source to destination. You have 2 of our routers in the middle. You could have many. Let's say you have 2. It doesn't matter what the underlay is. This could be MPLS, internet, LTE, VSAT, any sort of connection. WP1 and WP2 are the interface IP addresses of the routers itself. We're going to use that for forwarding this, like I mentioned. Let's say you want to send packets from source to destination. Like I said, we are a deny by default or a firewall as well. So deny by default router or a firewall. In the sense we are the opposite of a router. You have to have policies to forward packets rather than having ACLs to block packets. You don't need to have ACLs in our case. You just have firewall rules. Similar to that, you have service rules in our routers. When a new session comes in based on this 5 tuple, we figure out, have we seen this session before or not? Let's assume we have not seen this session. This is a new session, and we want to create state for it and have it forward traffic. We would, of course, check if it has policies associated with it. If it has no policy associated with it, we would drop packets. We want it to work like a firewall. We want to be a zero-trust network. There is no way you can spoof the router into believing, hey, this is a malformed packet, just forward it somehow. The router would say, I just don't have a service route or a route to forward you. We have to create a route first and have a valid policy for it to forward traffic. Let's say this has a valid policy, and we want to forward this traffic. What we would do is we would take the source and destination IP addresses from the packet, and we would put it in the metadata portion of the payload. This is the extra information we are adding to the payload only in the first packet. The metadata is signed and authenticated so that no one can tamper it. We then do a NAT. The NAT basically changes the source and destination IP addresses of the packet to WP1 and WP2. So now every router in the middle is thinking it's sending packets from WP1 to WP2, the waypoint 1 to waypoint 2. That's how we control the path in the network. You can have a series of waypoints, and you can control the entire path if you wanted to. Finally, we apply any other policies associated with the session. For example, if we want to encrypt it, we want to do some QoS, we want to do anything else, we would do all of those functions. We would send those packets out. Every router in the middle thinks it's sending packets from WP1 to WP2. It forwards that traffic. When, of course, it reaches WP2, we extract the metadata. We know from the metadata what the source and destination IP addresses are. We do a NAT. The NAT changes the WP1 and WP2 to source and destination, and the packet is sent towards the destination. This way we establish, at this point, these 2 routers will keep state for that flow. They keep a state telling it how to NAT packets with the packet number 2 to N, how you do that, how you keep state, how you forward things, how you NAT it back. The advantage of doing this is the destination never sees a change in the packet, what happens in the network. If there is link failures or node failures or any sort of failures or session migration, we migrate from, let's say, internet to MPLS or to LTE or any other pathway, that is always hidden from the destination, any change in the network. The reverse path also is guaranteed. Now the routers know that if the reverse traffic, they have to send it from WP2 to WP1. This establishes symmetry of paths in the network. By having a symmetrical path, we are able to better control QoS and everything else in the network itself. This is how the routers keep state and forward traffic. Any questions on this before we go to what the benefits this brings now?
So you talked about the first packet that comes through that sets up this state. How then does return traffic and the traffic following know to maintain that state? How do you identify that flow then?
Absolutely. So what it does is basically based on the 5 tuple, which is the source, destination IP addresses, the port protocol, the destination source and destination port, and the protocol, the routers keep state that, hey, anytime you see this 5 tuple, you do NAT this way and you send this packet out, and whatever other service associated things you have to do with that, for example, security or anything else. And in the reverse flow, they do the reverse. They keep that state as well. Any packet going from destination to source, now you NAT it this way and send it back.
Right, but your state table, when traffic comes in, let's say it's the third packet, not the first, how does the receiving router know which flow it's part of?
So from the 5 tuple, because now when he sees anything, let's say the receiving router here sees WP1, WP2, and he has picked a destination port here on this router. So from that 5, he knows it's a unique flow, and he identifies that.
So there's a unique port assigned to each flow.
Right. So when
the originating router then sends to that port.
Absolutely. So what this guy will do when the source router, when he knows he has to send traffic to this guy, he picks a combination of WP2 and the port, unique port address, so that we know the combination.
And those ports are transient. Like if the flow is done, that gets torn.
Yeah, we have a reserved
that port number.
Absolutely, we have a reserved set. I mean, in the sense we use a part of the reserved set. And not the next session, but the session after that, they're going to go in more details on which ones we pick. But you're absolutely right. We will pick a unique so that we know this session is unique. Otherwise, we won't be able to distinguish between the sessions.
Yes. And that's why we say it's session-oriented network.
True. It's because it's session-based. Per session, we will do everything.
Are you looking into the state of the underlying transport protocol as well? Are you looking for a SYN packet in the first thing?
So you're right. Yeah, we do keep a state machine. We do follow the TCP sync ACK and everything else because we also keep that in mind. So if we don't see a flow for a while, we know how to, or if we see a fin come back, then we know we can delete that state. For UDP, we maintain a timer. After a while, when we don't see any more packets, we will reduce that. We will take away that state. So we do use that flow. We do participate in the SYN ACK exchange so that we know what is happening. Also, we use it for many other things in the sense for TCP optimization and other things, other features we have, which we'll cover later. But we want to follow the TCP SYN ACK, window sizing, and so on.
The first segment you receive is a mid-flow segment. Is that okay, or is that an error condition?
It is possible that you may receive mid-flow. For example, it's possible in the receiving side, let's say there is a failure in the network, and now you choose another path. In that case, it may come mid-flow from another interface. But because he has state, he knows that this is mid-flow for the previous session. He recreates it back.
I'm imagining a network convergence event over on the source side. I mean, maybe that first 128 router didn't see the beginning of the flow because it took some other path.
By default, using the TCP state machine, we would project. No worries. By default, we'll use the TCP state machine and reject the packet, but we have a setting that can override the TCP state machine if that's desired, and that can be set on like a per service basis.
Gotcha. And I think I understand you maintain path symmetry between waypoint addresses.
That's correct.
Across that GLAIC.
The more routers you add, the better symmetry you get. Yes.
Sure.
Yeah.
How do you enforce symmetry on the return path from the host? I mean, what if the network on the right side believes there's a better way to reach back to the source that's not through 128 routers?
You mean if it bypasses these routers instead of sending it back to this router?
I have like a real circuit that for some reason is chosen as the return path.
It's possible that the destination may choose. In that case, it will be established as a different flow. We will have two flows in the sense when it comes back here, he will think there's another session state and he will forward based on that. It doesn't have to be that they have to be symmetrical, but it will keep both a state for one direction and a state for another direction.
Okay, so that's okay too.
That's okay too.
That's
yes.
not an error.
Yeah.
Thank you.
Let's talk about network virtualization before we talk about the benefits. Like I said, we have a very unique data model, and it's going to be covered in more detail in one of the sections here. But having said that, what we want is we want to drive things towards services. Like I said, we don't want to always configure 10.10, 1.1, and so on. Ultimately, That's what the network does, and that's what the routers do. They obviously work on IP addresses, but to configure them, what we have done is we have got names. And how it works is you can have tenants. Tenants are basically groups of users. They can be based on interface address, based on virtual interface address, or anything else. You can define ways how you identify tenants. We're also working on, you can do that from Active Directory or LDAP and other things. You can identify tenants. But having said that, there are groups of users. For example, sales can be a tenant. And service is what the tenant has access to. For example, it can be a Facebook, it can be Salesforce, it can be your own private application, it could be IP phones or anything else. Service routes are basically where that service is located. For example, it could be located in your data center, it could be located in a public cloud or anywhere else. The advantage of doing this, of configuring networks this way is we can have policies per session, unique policies per session, and we can also make it location independent in the sense, for example, if I have my own data center and I have a service hosted there, I tell everybody, hey, send sales traffic to that database, which is located in my data center. Once I see that the load is increasing on the data center, I could enable the same service in, let's say, AWS, and all the routers in the network would understand, hey, now I have a new service. For the same service, I have a new service route. It's in the data center. I can load balance to that as well if I want to, and so on. So it makes it very elastic. It makes it mobile. It makes it location independent. And that's how we configure routers in our policy. Also, these policies are global in the sense, once you tell any of our routers or the conductor, which I'll come to in a second, the conductor, which is basically telling every router where everything is located, they all understand how to forward traffic based on that. You don't have to go and configure ACLs or policies per router itself. You don't have to do that. It's a global data model. If you look at the way networks are configured today, you need to have VRFs for segregating traffic. You create VRFs, you import-export VRFs. You do encapsulations and tunnels. You use route distributions. You have firewall rules, NAT rules, ACLs, and so on to configure networks. For example, if you, let's say, have users, sales, games, phones, and they have to access services which are on this side, and we're going to use this example in some of our demos as well, you would create VRFs for each of these. You would put them in VRFs. You would make sure that all the routers understand those VRFs in the middle, set policies accordingly, and configure the network. It's a very flat way of configuring networks. You have to go and configure everything on its own. It's not end-to-end, it's not directional, it's static, and it's a flat topology. If you were to do the same thing in, let's say, the 128 context, you would have it this way, in the sense you would have your authority, which is your global authority, and then you would have tenants and who have access to services. And all routers understand this logic, and they forward based on this. Even our management tools and everything will show you in this graphical way. You can add, modify, remove things. For example, if I added a new service here and I gave it to surveillance, you would see another leg here which would give that access to the service. The advantage of configuring things this way, it's end-to-end, it's directional, it's dynamic, and it's hierarchical. It makes it very easy to configure networks. You don't have to go and make changes per router and so on. Any questions on services before I go to the routing functions?
So I guess I do have a question on how are you determining, so I guess the question here is identity, right? So you're identifying services and you're identifying sources. I mean, is that all just based off of IP ranges, or is there any more intelligence in how you're determining identity?
Identity of the users, we have integration with LDAP and so on. Also, you can use that for doing, we have some integrations with NAC, Network Access Control, like Genians and others, whom you can have endpoint agents, and we can take feedback from that agent and also identify traffic. And of course, the traditional ways by doing interface IP address and so on, all of those exist as well.
Okay, so you do have some deeper options, so you based off
right.
How a user authenticates to the network. Or...
Right. We do have some other capabilities. I mean, I wouldn't say we have integration with all NAC clients, but many, yeah. And as required, we will add more.
Okay,
it's true.
How does the router deal with traffic that doesn't originate from it? So, like, if a client or whatever initiates a Zoom call with somebody behind one of your routers, does it just treat it as a regular session, or?
Right. So if there are a couple of cases which may happen. One is, let's say there's only one 128 on the path. In that case, it would not do this. It would work as a normal router. It would forward packets. Because it already understands routes, it would not add the metadata. It would not do SVR. It would work as a normal router. The other option is, like he mentioned, if it bypasses our router by some sort, the client bypasses like Zoom and other things, they can do intelligent port mapping to bypass. If they do that, then it'll be established as two separate sessions. And it would forward traffic that way. It would not add the SVR metadata if it doesn't see the upstream 128 on the path. That's true. Let's talk about some of the functions now, because we are not having tunnels and we don't have this overhead. What would happen? For us, we have fail-safe delivery at all time. In the sense, any failure, we monitor all paths in the network using BFD, using an enhanced BFD. We know delay, jitter, loss in every way. If there are sessions on that path, we can color the sessions, and from that we know how much delay, jitter, loss is on those paths. Anytime we see a degradation or a link failure or a node failure, we move sessions to other paths. In case of tunnels, when you do that, you would have to reestablish a backup tunnel, or you have these backup tunnels up all the time, which introduces scale challenges and so on. In our case, failovers are always sub-second, in the sense, anytime there's a failure in the network, we would go through and reestablish on another path. And since we use in-band signaling, even if we go through any firewall changes or any NAT devices in the network, we recreate those sessions back. We don't see any issues because of change of IP address or anything else. And the advantage is immediate reestablishment in any scenario. It doesn't matter if the flows, because we don't have any tunnel establishment time or any delays. Failures are always sub-second in our case. As long as there's a path, it would find another path which meets that SLA and fail over to that network.
So I'm going to take the conversation back up a level. It's not related to the current slides. I'm getting the flavor for the capability, the technical capability of the solution. One of the things that I'm a little bit unclear, and I might have missed it earlier, is it's a very ambitious product from a capabilities perspective. So most of the time when competitors are coming in and talking to me and my clients about this type of solution or a similar SD-WAN solution, it's very use case specific, replace your MPLS, do some reduction in overhead for VPN. What's the predominant use case for when customers are considering this solution?
So there are a couple of cases when it's a general purpose router, so it can be used in all scenarios. But having said that, there are a couple of scenarios in which the solution really shines through. One of them is when there are a large number of sites. For example, if there are thousands of sites and you want to make a full mesh of tunnels, let's say you have 5,000 sites, it's impossible for any branch router to maintain 5,000 times 5,000 tunnels per branch router to talk to everybody or make a full mesh. So then you have to do hub and spoke. It increases complexity. At that time, because ours is an any-to-any connection at any point of time, that provides high scale and high performance. So when the number of sites are higher, this solution really shines through. The other case is when there is low throughput links like satellite or any low latency, or any low throughput links like DSL or others. Because we don't use, we're not using tunnels. I'm going to do a comparison later on the overhead sizes and so on. But having said that, you'll see a 30 to 40% reduction in bandwidth usage because we're not adding a full IP header, which tunnels do. The advantage of doing that is obviously we will lower the bandwidth usage. You will see better performance of applications, so congestion will be lower. So when low throughput links are there, this solution really shines through. LTE or other connections are there. It really works really well. So those two scenarios, I would think it works the best. Also for multi-cloud scenarios, we were just discussing yesterday that since cloud providers, they charge you based on the size of the instance and also based on the amount of traffic you will send outside the network. If you reduce the bandwidth usage by 30%, you automatically pay them less. So those are the scenarios in which this really makes a huge difference. The amount of data you're sending is high, low throughput links, and of course, large number of sites.
So at some point, we're going to talk through kind of the business case of why because as I'm thinking through, as you're trying to displace incumbents and also compete with other SD-WAN providers, most of the solutions out there are additive. And then to say, I'm going to replace my general purpose router with these solutions, that's a scary statement to make to most enterprise customers, especially when you're talking about in the thousands. Like there's so much that goes into that decision. I'm just really struggling with kind of the business case around why I picked 128 Technologies as a general purpose router.
Normally when we go talk to a new customer, we're not out there trying to do a full-scale swap of their entire network with 122 routers. I mean, if they want to do that, we're happy to do it, obviously. Right. But we usually try to seek out what are their real problems in networking, like what sort of a problem, what are the hardest problems that they have to solve, and help them solve that problem. And then from there, obviously gain traction and see where else we can deploy. But we're not out actively seeking to replace somebody's full-scale network. We'll work with existing legacy routing frameworks, other routers, Cisco, Juniper, other products. We want to go where we want to be in the network where it makes sense and where we can help solve specific problems.
And I think that's the one other question I had that you can get back is where it makes sense. Like, so traditionally, I see actually WAN at the WAN. But again, general purpose router, I can put a general purpose router anywhere on my network. Like, is the WAN the number one use case that you guys going after? Or are we seeing these in other parts of the network other than the WAN?
Right. So we have actually some use case in the second half of the day. But having said that, WAN is of course one of the big use cases. Multi-site connectivity, any edge connectivity is big for us. Cloud, multi-cloud is big for us. Data center interconnect or hybrid interconnect, any sort of data center movement is. Those are the main areas where we are being used today, and the deployments are large in those areas. Having said that, some also use us for internet peering and so on, but those are a little more rarer, I would say. Today it's a little more rarer, yeah. We also have all sorts of existing functionality like you see in traditional routers. QoS, you can do great QoS with our routers. You have granular control. Since we don't aggregate things into tunnels and just copy the toss bits out, per session you can define any sorts of SLAs. You can tell what to do with that, and we'll do QoS for that. We have great load balancing capabilities. Like I said, you can create elastic policies, so you can define where loads go, and it'll balance those loads. We have different kinds of round robin, hunt, different kind of policies you can apply to do 50-50 split, fill this data center up first, then others, 70-30, any sorts of all that kind of distributed load management. We also have a lot of man-op capabilities in the router itself. We can do TCP acceleration to improve performance, so you don't need to have caching and so on or other devices doing that. You can do that in the routers as well. All the session-based capabilities you can do in our router today.
Hang on, did you just say caching on the WAN op stuff?
Only for per session basis. Yeah, we don't do CDN, but it's not caching for future sessions. We would not do that. But yeah, what we would do is we would do a fast stack, and we would maintain packets for that session so that we can replay them quickly.
Interesting. Okay.
Yeah. Zero trust security. There's a session on security later on, but I just wanted to touch upon some of the capabilities we have. Like I said, we are a deny by default router. So the traditional way of doing is based on perimeters. You put firewalls in the perimeters, or you take your traffic, you trombone it to a cloud gateway where you scrub the traffic and you send it out. In our case, what we want is every router to be the firewall itself. And like I gave the example, today you can bypass firewalls because you bring your own devices. Devices are moving. You can bypass firewalls by doing that. In our case, what we want is every router is the firewall itself. So for every router itself, it'll do hop-by-hop authentication. So for example, if you had packets going towards one direction, if they were malformed, we wouldn't send them to the endpoint, and it would not cause a DNS attack or a DOS attack. We would drop them as on the source itself. We have another feature which is called adaptive encryption. Basically, it detects TLS and IPsec encrypted flows and doesn't re-encrypt them if you want. You can set policies that 80% of the world's traffic today is already TLS encrypted, so you don't need to re-encrypt them. That doesn't make any sense. It just takes a performance hit if you do that. So we can detect it and not re-encrypt it. We are a distributed firewall. We have ICSA certification. We just got it last month. We are a fully layer 2 to layer 4 ICSA certified firewall. We deny by default in the sense just like a firewall, you need to have rules per services. The rules can be very generic. You can say send all traffic to internet, or you can say very specific things like only send sales traffic to Salesforce and so on. And of course, we follow directionality. I already gave some examples how directionality helps us detect things, and we don't forward traffic unless it's in the right direction. Some of our compliance, we keep getting asked. Encapsulation doesn't give you encryption. Encryption requires AES 256. Just encapsulating a packet is not what gives you encryption. We also do NATing, so it's the same as IPsec. We masquerade traffic. In fact, I would say it's better than IPsec, because in IPsec you can see the inner header. In our case, there is no inner header. So you save bandwidth, and also you get all the encryption capabilities. We can do AES 256, any other AES 128, HMAC SHA 256, any other things. We are FIPS certified. We also have PCI and FISMA compliance. We have also ICSA certification for PCI compliance, so you can build PCI compliant and HIPAA compliant networks using us. And like I said, we are already a corporate firewall certified product.
So before we go into on the firewall topic, one of the big challenges with firewalls is managing firewalls across multi-cloud concepts. So, what's a OS instance in AWS is not the same as what's an OS instance in Azure, and that's not the same as a VM instance. So while I may have the same general firewall across the infrastructure, I don't have the same endpoint concepts. What are you guys doing to help with that, applying a consistent policy across multi-clouds?
Yeah, I mean, one of the challenges is consistency across multiple clouds, because everything, like you mentioned, everyone does it a slightly different way of configuring things. In our case, all the policies are global, and when we do the demo, you'll see. So when you make a change, it applies globally to all routers in the network, or all routers in the authority, in the group of routers you have. So it's always consistent across the group of routers in the network. They'll all follow the same policies, same service models, in the sense directionality, any restrictions you have, or any QoS settings or anything else. It would follow that all the time globally. So the advantage of doing that is on a per router basis. You don't have to go to AWS and configure things separately, or to go to Azure and configure things separately. If they're both in the same authority, in the sense under the same domain, they would be configured similar way, and they would work similarly. So that's how we achieve consistency and policy across multiple clouds.
Okay, so we're gonna go deep into.
Yeah, we'll show a demo, and actually, yeah, we have a demo on that. Yeah. Service assurance. So we monitor all paths in the network, different paths in the network. If we have traffic, like I said, we'll monitor that traffic. We can color the traffic and monitor it. If we don't have traffic, we can use BFD to monitor the path. We use a little enhanced version of BFD, so we get delay, jitter, and loss. We have sequence numbers in there, so we can get delay, jitter, loss on all paths. We also know the loads on every path. So what we can do is, anytime there is a session which needs a certain amount of SLA, we put it on that path. If, let's say, things change and session degrades, we would immediately modify. We would change its path, and we would send it over another path in the network which meets that SLA. If there's no path which meets the SLA, we'll use best effort, and we'll create an event. We'll tell you that we are doing best effort right now. But failovers in our case are, like I mentioned, a sub-second all the time. So any degradation in path, you'll see instantaneous failover to another path in the network. We can also send the same packets over two paths in the network. If it's a very high-value traffic and you want to make sure that no node or link failure on any path causes any degradation of the flow, what it does is basically this router will remove duplicates and send only one of the paths out. We can do that for heterogeneous networks as well. You can duplicate flows. Before I sum up and let others go into a little more detailed analysis of what the routers do, all of our routers, they have capability. You can access them via CLI or a GUI. Each of the routers, they have a GUI itself. You can go into that and you can configure things. We also have a network monitoring and management tool called the Conductor, the 128T Conductor, which itself is based on our REST and NetConf APIs. You can use that to manage all of our routers. The tool is mainly an orchestrator, in the sense it doesn't participate in any routing decisions or doesn't need to trombone traffic. Routers do not need to wait for it. It only uses it to disseminate policy. So it tells everybody what the policies are. You can also take our APIs, you can integrate it with third-party tools, any existing third-party tools you have. You can also use that for doing big data analytics. You can export the data and use it for doing big data analytics using Splunk, Data Logic, or other things. And of course, you can use any DevOps tools to manage our routers. You can also manage our routers using OpenStack, VMware vCloud Director. Many of our SEs use different tools for different customers. Deployments, Puppet, Chef, Salt, Ansible, they're all used to manage our routers.
That means you're exposing an API that any of those devices can consume?
Yeah, so it's we have a Swagger API which you can use. You can see all the commands, and yeah, you have to make the right calls to make those calls, and of course the routers will do that. Yeah. Flexible deployments, just to give an idea of finally, now we talked about all of this thing, we talked about all the software, how do you make it run, and how do you do what is required. The speed or the performance of the routers depends on how many cores we will have. So for example, I have taken some examples to give you an idea of the performance of the routers. On a 2-core, let's say an Intel platform, on a 2-core Intel platform or a 4-core Intel platform, we will do about 10 meg to 1 Gbps throughput. It's very high performance because, like I said, we use DPDK, we program hardware, so everything works at line rate. The 2-core or the 4-core devices, I don't know, they are about $350, $400, depending on the platforms you choose. If you go for higher end, let's say for Intel Xeon processors, you can use a 10-core, 12-core Xeon processor, and you'll get about 10 gig of traffic through it. The higher you go, let's say you use 22-core, you can get about 80 gig or 100 gig throughput through it. Obviously, Xeons give you much better performance than the Atoms, the low-end Atoms. But it depends on the number of cores you will have. It pretty much linearly increases with the number of cores you give our software. If you service chain us with somebody else in the box, like for example, a security VNF or something, then it depends on how many cores you assign us, how many cores you assign them. Depending on the cores you assign us, you'd get that much performance. And the same thing for our cloud deployments. Depending on the size of the instance, the size of the EC2 instance or the size of the instance you choose, that's the performance or throughput you get in the network. It scales linearly with the number of cores you give us pretty much. Partnerships. Obviously, we have a lot of partnerships for doing different kinds of things. We have technology partnerships with, of course, we use Intel. We are big on Intel. We have partnerships with Palo Alto, Zscaler for service chaining, for higher layer 7 functionality, security functionality, and so on. We have hardware partnerships with all of these partners. You can choose from any of them. We can recommend you to our partners as well, who can sell it as an appliance to you. We have cloud partnerships. We are available in all the 3 marketplaces. You can go to any of their marketplaces. You can search for the 128T networking platform, and you'll see us. It's zero-touch deployments. You can just deploy them there. We have support partnerships for delivering services and support. We have managed service partners who deploy us in different parts in the network and in different geographies as well. And we have sales partnerships with many of them who enable us, who use our solutions in their managed service solutions and so on in the network.
On the cloud deployments, that just means I'm deploying a 128T endpoint, a router effectively into one of those clouds, my VPC. What?
That's correct. Okay. And you can use it to connect to your branch sites or anything else, or between the multi-clouds, you can do that.
So there's no special partnerships you have?
Oh, we do have, yeah. So we have co-sell partnerships with Microsoft and others. So they recommend us in their solutions. We do the same. We have co-sell partnerships with Microsoft and with AWS. Yeah. An example of some of our deployments. These are some of the public reference customers we have. I took a couple of varied ones to give you a flavor. We're going to talk more about the use cases in the second half. But a quick introduction is one of the customers we have, CMC Networks. They are the largest Pan-African and Middle East carrier. They use our software today to provide enterprise connectivity to their enterprises. One of the challenges they face is because they're located in Africa, the bandwidths are not very great in many parts they operate in. And to do that, they have to use, and they have SLAs with these customers, so they need to make sure they meet those SLAs. By using some of our solutions, they have been able to guarantee that they meet those SLAs. They're able to support thousands of sites. And since we don't use bandwidth overhead, it improves their connectivity, improves their speeds, removes congestion. They actually have done an analysis in which they say that just because they don't have to pay the penalties now, they are able to recover most of their costs just because they eliminated penalties. Bard Materials, they're a construction company in the Midwest, in the tri-state area. They have remote sites which they need a video feed to come through all the time because they monitor the number of trucks going through that. That's how they need that feed all the time, otherwise they are in the dark. They were able to use our solution and advanced QoS, and they have LTE connections and point-to-point wireless, which they use. And they have seen a lowering of 50% TCO. And they believe that there's a saving of 1K per truck per day because they're now able to judge better how much materials they'll get, what will happen in the network, and so on. Finally, Revation Systems. They are a unified communications provider to 300 hospitals in the US and Canada. One of the challenges they face is that the middle network, which they don't control, may have issues, and then the quality of experience degrades for the hospital. By placing our routers at the hospital sites and by using multi-path connectivity, by using LTE as backup and so on, they're able to bypass the problems they face with the service provider in the middle, and they're able to guarantee SLAs. They actually say that now they can extend their SLA from the data center to the customer site. And because they're able to use they have done some integrations and they're able to onboard customers faster now. They have improved uptime and SLAs, which they have. Overall, before I hand it to the next presenter to go in more details on the data model, I just want to sum it up by saying, overall, the 12080 networking platform, we do a couple of things. We make things simple. We remove tunnels and overlays. We are completely software-based, so you can use white boxes for deploying us. It makes it very simple to use. We are agile. The reason is because of the service-oriented nature of the way you configure things in our network, in a network built by us. You're very agile. You can add, remove, modify services on the fly, which makes it very useful. We follow a zero-trust model. We can authenticate, encrypt, and segment traffic. For us, each session itself is a separate hyper-segmented flow. You don't aggregate things into tunnels. You don't do any of that using our solution. Because we use no overhead, you have bandwidth savings in the network, lower congestion, high scale. We already spoke about some of these things. You can do dynamic optimization. And of course, savings based on all that, because you're reducing the bandwidth usage and you have improved, and you have reduced your cost of middle boxes and hardware. You have better cost savings in the network. Any questions before I hand it to the next presenter to talk about the data model?
Yeah, you got 5 minutes left, so I'm going to try and use up all.
Yeah, let's do that.
So.
Nice.
All right, so one of the things that I'm not completely understanding is the end-to-end value of the solution. As I'm looking at modern solutions that are as aggressive as this, they're taking a look at all the way from the endpoint in the cloud through the wide area network and the management of that. So can you tell me a little bit more about the management story of why I would choose a 128 technology solution when I can get an end-to-end solution that kind of has an end-to-end vision of traffic and network flow?
One of the things we always notice is that even though, like for example, even though you have two routers in the middle and you're sending traffic, people say, oh, I'm sending 10 gig. Yeah, I'm sending 10 gig. But most of them are retransmission, so the application doesn't see those benefits. But the advantage of our solution is we monitor everything on a session level. So per session, we can tell you what happened in the network. We monitor all packets in the network, what was sent in the traffic, how many were retransmitted, how many were dropped, and so on. So you have excellent visibility using our solution into what happened in the network. You can generate reports. You can actually use those reports to tell customers, hey, this is exactly what I did with all the packets you gave me. This is what happened in the network. So you actually have very good monitoring of every path it took, what happened in the network, which router, which packets were dropped, or whatever, in a QoS, what happened in the network. Regarding the end-to-end story, I already mentioned, we do use integrations with others to provide an end-to-end story. If you do have parts of the network which are of course not with 128, then you can extract the data from our routers and then extrapolate it and combine it with others to do big data analytics or whatever, merge with other things in the network. But we do have great analytics or capabilities to analytics because of the session data we maintain. Like per session, we know everything what has happened in the network, and we can tell you what's going on. And we also have some advanced capabilities, which is the team is working on, and they'll talk to you in the second half. It's called STEP. Basically, we'll have a central repository which will have all this data, not only the data on what happened with the packets, but also performance and SLA data for different links. So at any point, it's like a heat map. You can see what was going on in the network and what happened in the network at different times, and you can replay them. You can see alarms and events happening, so you can judge based on that. Hey, 5 o'clock, just like Google Maps tells you, tomorrow 10 o'clock traffic is going to be like that based on all this historical data you have. You can tell tomorrow 5 o'clock what's going to happen in the network or what sort of congestion you'll see and so on. They will talk to me a little more about that stuff, the capability.
So operationally, everyone loves the white box story until they have to actually deploy and manage white boxes. So, one of the advantages of a sealed solution is that when it comes to alerts, operating system management, all that stuff that makes a network actually work, what are some of the tools and mitigations you guys give us for when it comes to hardware failure in the white box and managing that? Is that managed separately, or is that part of the 128 solution?
We are trying more and more to take that on in the sense currently we have all capabilities in our solution itself to see memory usage, throughput, anything happening with the hardware itself, like how much memory is being used, if there's a memory spike, if there's CPU overload, if there's temperature overload, anything happening. We take all that data and we show you in the 128. We want to give of course, like an appliance-like feel to it, even though you're using white boxes. Once you put our solution on the white box, we wanted to have like an appliance-like feel. So we do take all that data and show it to you, including, like, for example, if you're using LTE, we'll show you stats from the LTE driver and what happened, how much is the throughput and everything, what frequencies are being used. We do have those APIs now, and it shows you all in our product itself. Having said that, sometimes the rare case it does happen, people go into Linux and try to do things, but we are trying to avoid that and take more of the functionality and give appliance-like feel using our software alone. Go ahead, sorry.
How does this platform work in a country like China that blocks VPNs?
Currently, we won't get blocked if that happens, but having said that, it's not our intention to bypass the security settings they have or anything like that. But it's true that we don't use VPNs, so we would actually go through their network today. But having said that, that is not the intention. It's just the way we work. We don't use VPNs. Having said that, of course, they can use IP addresses and so on to block us. But today, yeah, we have seen instances where it is possible to use it in those functions as well, yeah.